In this unit, we're going to talk about SAS, the Supervisory Attentional System. In the first video, we'll talk about SAS as short-term memory. In 7.2, we'll talk about SAS as working memory. Remember, from the last unit, we said that there are two attentional systems. Attention system 1 with these three things, and attention system 2 with selective attention, attention as a resource, and SAS. So SAS is nothing but short-term memory or working memory. Short-term and working memory are different conceptions of the same construct, SAS. What is a simpler conception of it? Working memory is a more complex conception of it. We'll talk about SAS as short-term memory first, then we'll talk about SAS as working memory. Both refer to the same SAS. It's just that we are conceptualizing in a simpler fashion first, then a more complex fashion. We'll also talk about the need for developing a complex conception. Before we do that, we need to know what SAS is. So what is SAS? Well, SAS is supervised attentional system. It is a controlled attentional process. And you've heard this term before, short-term memory or working memory. They all refer to the same thing, SAS. It's a form of controlled attentional system. I know it's counterintuitive to think of a memory system like working memory or short-term memory as a controlled attentional process. That's what it is. And there are other names to SAS, not just short-term and working memory. Short-term store also refers to SAS. Temporary memory also refers to SAS. The objectives for 7.1 talk about SAS in general, then talk about SAS as short-term memory. What is this SAS in general? As we said, it's a controlled attentional process. So when we say SAS, this is one part in your system where the things you're aware of happens. It's a seat of consciousness in that sense. If your thing happens and in your mind and if you're aware of it, it invariably happens in your SAS, the supervised attention system. Everything we are aware of happens here in SAS. And everything that we process at any given point of time, irrespective of whether it is active to your awareness, available to your awareness or not, it happens in this system, the SAS. It's a working system. So what are the characteristics of SAS in general? Well, SAS is a part of the attentional system too. When you're talking about attentional system too, you know that as a resource, attention is limited. So is SAS. SAS is limited. Limited in what? It is limited in capacity and limited in amount of time. In other words, SAS, whether it is short-term memory or working memory, it is limited in how much information it can hold and for how long it can hold information. It applies to both. But first, we'll talk about SAS as short-term memory. Then we'll talk about SAS as working memory. Let's talk about SAS as a short-term memory and its limited capacity. The idea of limited capacity of short-term memory was first proposed by George Miller. Do you remember George Miller from History of Psychology, where we talked about the conference in 1956? Where the three important presentations presented on the third day of the conference in 1956, and one of those presentations was that of George Miller. By the way, what were the other presentations? You're right, the others were, one was by Chomsky, Transformational Grammar, and the other one was Logic Machine Theory by Newell and Simon, right? That laid foundation to cognitive psychology. The same presentation by George Miller, that was the first presentation or first paper to talk about limited capacity of short-term memory. On average, people hold 7 items plus or minus 2. It changes from person to person, but overall average number of items we tend to hold in our short-term memory is around 7. Later research has suggested that it's actually even lower than that. It's at 4 or 5 items plus or minus 2, not even 7. Think of short-term memory as a bottleneck. Remember, when we talked about sensation perception, we said your sense organs, for instance, your vision, your eyes, capture 76% of information. 76% when compared to the information out there in the environment that is in your visual field. 76% of information is held at least for 250 milliseconds in your sensory memory. Well, your long-term memory holds unlimited amount of information, theoretically at least. The system that connects sensory memory with long-term memory, if you remember from our discussions from the big picture videos, only holds 7 items. It's like a bottleneck in that sense. And for that reason, if you remember, sensory memory holds 76% of the information. Short-term memory can only hold so much of information because of limited attentional resources. You need a subsystem that can help you move from a lot of information to manageable information that can be perceived in short-term memory. Guess what that process is called? You're absolutely right. There's a tension. So we hold only 7 items in our short-term memory. The question is, can we overcome this bottleneck? Can we hold more than 7 items? Let's see if you can do this. I want you to go over this task. I'll show you a list of letters, in fact, a string of letters in the next slide. I want you to remember as many letters as you can. Here we go. Please don't write it. Okay, I want you to recall now on a piece of paper as many letters as you can. I suggest you pause here for a second, then come back, and we'll talk about the answers for this and see how many items you remember. Well, I hope you pause the video and recall how many letters you remember. It's typically 7, maybe 9, maybe 10, around 7. Some people remember fewer items, others remember more, but on average, it's around 7. So the question is, can you increase this number? Can we overcome this bottleneck? Can we remember more than 7 items? Well, let's try another list of and see how you do this now. Are you ready? Another list of letters. I want you to remember as many as possible. Here we go. Are you ready? Okay. Okay, recall now. Yes, you're 100% accurate in the second case. In the first case, though, you were not. You only remember 7 or on average 7 items. If you see, these were the same letters. This is a list of letters presented to you the first time. The second time, it's the reverse. Do you see that? The same University of Southern Indiana. But in the first case, you only remembered 7 items, but in the second case, you remember all the items. Why is that? I want you to think about it. Pause the video here, think about it, and I will talk about it in the next slide. Well, the reason why you remember the letters in the second task is because you have grouped those items. University of Southern Indiana. Those letters were grouped to form one chunk that meant something. University of Southern Indiana. This grouping of items based on some criterion. In this case, the criterion was a word has some meaning to it. This grouping of items is called chunking. In other words, you're taking items but grouping them based on some criteria. You are processing these items by recoding them, by chunking them into groups, then trying to remember this as a unit. Instead of 24 items, you have manageable chunks of, say, 3 or 4 items with 3 or 4 items in each chunk. Selected list of items, it might not be possible for us to chunk them. So it takes a lot of time to recode them, chunk them, remember them, and then recall. As we know, sensory memory holds information for a fraction of a second. For the visual sensory memory, it is for around 200 to 250 milliseconds. In long-term memory, though, information is held forever. Now, in between those is this short-term memory that holds information for longer than a sensory memory would hold. For visual system, though, which we are more interested in, information is held for 15 to 30 seconds. And after that, new set of information enters the system again. Have you seen this movie Memento? This person has short-term memory loss. The person can only hold information for 30 seconds, and he cannot move the information to long-term memory, so he has to redo the process. The point I'm trying to make here is there is a limit in terms of amount of time you can hold information in short-term memory. It's not just the amount. For the amount, you can always chunk. But what about the time? What can you do to overcome the bottleneck of time? Can you hold information in your short-term memory for longer than 30 seconds? Just think about it. Before we move on to the next slide, where we'll talk about different ways of holding information for longer than 30 seconds, this is what I'll ask you to do right now. I'll give you a sound that you might not have heard in your life, so there is no way you can make meaning out of it. I want you to hold this information in your short-term memory for longer than 30 seconds. Are you ready? Okay, let's try this. Kashmora. I'm going to say this one more time. Kashmora. Hold it. I'm going to ask you. Hold it. Okay, what is that word? What is that sound? That's right, it's Kashmora. Well, how did you hold that information for longer than 30 seconds? Well, you repeated that information in your head over and over again, right? Okay, so one way to retain information in short-term memory for longer than 30 seconds is through maintenance rehearsal, and that's what you did, where you repeated the sound in your head over and over again. It's rote rehearsal where you're holding the information and just repeating it. There is another way of doing it. It's called maintenance rehearsal. It's similar to chunking, but it's not, in the sense that you're trying to connect it with something you already know. For instance, some of you might have done this. When I say cache more, where you probably have divided that and tried to connect it to something you already know, like cache and more, cache more, hash more cache more, right? You're trying to break it down into cache and more. If you did this, then the way you held information in short-term memory for longer than duration is through elaborative rehearsal. Elaborating the information in short-term memory will also help you hold information in your short-term memory for longer than the duration. In fact, it's not just holding information in your short-term memory for longer than its duration, but it also helps you move the information to your long-term memory when you make elaborations, connections to something you already know in your long-term memory. So these are two ways of holding information in short-term memory for longer than its duration. The next outcome is to put how information lost from short-term memory. Two different theories on how you would lose information from your short-term memory. What is the reason for losing information? There are two explanations. One is through decay. The other one is interference. Decay is when the information gets lost over time. You can see the traces of memory get disintegrated over time. It's just passage of time. And the information gets decayed. It's a decay theory. This particular explanation was reinstated by experiments conducted by Brown and Peterson using a specific experimental design called Brown-Peterson paradigm. We'll talk about Brown-Peterson task, what the logic of the experiment was, and how they concluded that the way we lose information from our short-term memory is through decay, which is simply losing information over time. In this case, it's 30 seconds. Now, another explanation for it is you're not losing information because the information is sitting there and getting disintegrated, but this information that is held in your short-term memory is replaced by new information, or it's interference. Interference needs other information to interfere with you holding information in your short-term memory. We talk about these two paradigms that looked at this explanation. One is the Brown-Peterson paradigm that suggests that decay is the way we lose information. The other one is the digit probe paradigm, which talks about interference as a way we lose information. It's a very interesting set of experiments, and it's beautiful. We'll talk about that in the next few slides. So let's talk about the Brown-Peterson paradigm. The Brown-Peterson paradigm is a very specific kind of paradigm. The main point of this paradigm was to make sure participants are not repeating the information in their short-term memory. So they developed the experiment to prevent participants from repeating the information because they wanted to see is the information in your short-term memory lost by passage of time. They manipulate time, but also not allow the participants to repeat the information. It's a very interesting, tricky situation. This is what they did, and this is what it means when you say Brown-Peterson paradigm. The primary task of the participant is to remember a three-letter trigram. It's very easy, right? Like G and T. If you're just given these three letters, you can repeat these letters over and over and try to remember it. That would be easier. Well, to prevent that, what Brown and Peterson did is after presenting these three-letter trigrams, participants were presented with a three-digit number, for instance, 728. And the moment they get this number, participants have to count backwards out loud by three. First, they get three letters trigram, let's say G and T, then they see a digit, three-digit number, 728, then they have to start counting backwards right away. So you have to 72, 728, 725, 722, 719. Do you see that? How difficult it may get if it's continued? The aim of this task was to distract them from repeating these letters. They varied the length of distraction task. Either they did not count backwards, or they counted it backward for 3 seconds, 6 seconds, 9 seconds, 12 seconds, 13 seconds, or 18 seconds. And what was measured was the recall accuracy, averaged across several hundred trials. With the increase in delay, the idea was the accuracy also will drop, suggesting that information is lost over time. Shorter the distraction task, shorter the time the information had to spend in the short-term memory, and longer the distraction task, longer the time. And because they were not repeating the information, the only explanation they thought for these results was that the information got disintegrated, suggesting time is a factor in determining how we use information. As you can see, as the time increased, right, the accuracy dropped. In other words, if the delay was immediate, if they were asked to recall immediately, it was almost 90%. And if they're asked to do the distraction task for 3 seconds, it dropped. For 6 seconds, it further dropped, and so on and so forth. Passage of time the accuracy drops, suggesting that you're losing information as a function of time. And the only reason for that is the information gets disintegrated. Now, think about it. They manipulate time. Wow. And Norman in 65, they questioned this paradigm. The results of this experiment said, wait a second. Of course, with the increase in time, there is a decrease in recall. But is it just increase in time or there's more to it? In other words, is the distraction task just preventing participants from rehearsing the information, or the distraction task itself is acting as interference? Do you see the logic here? Is the passage of time also has a confound of interference of counting backwards? It's a very interesting question, and they try to find answer to it by manipulating both time and interference. It's very interesting, and I'm going to talk about this experiment in the next slide. So here's the interesting thing in the Vaughan-Norman study. Task is referred to as the probe digit task. I want you to pay attention here. It seems confusing, but once you get the logic of it, it all makes sense. So just bear with me here, and I'm gonna go over this slowly so we both are on the same page. Okay, this is what Vaughan-Norman did. Number one, participants were presented with random order of 16 digits presented digit at a time. They'll hear 7, 0, 8, 4, 1, 6, 0, 9, 5, 5, 3, 7, 2, 4, 7, 8. So each participant in a given file is presented with 16 digits. Okay. Now, here's the interesting thing. After the last digit, they hear a tone. When they hear, have to go back to that time when they first saw this probe digit number 8 and recall the digit that isn't presented after 8. Do you see that? Again, this is a probe which is presented definitely at the end of the 16-digit list, and somewhere here, in this case, the probe was, and there is no way participants would do which one would be a probe. Participants have to recall the digit following the probe digit. So they have to go back in their memory. They manipulated both time and the interference. The way they manipulated the interference was by manipulating the number of intervening items between the to be recalled number and the tone itself. You can see that, right? If this number is closer, then there are fewer items. If this number is either closer, then the number of intervening items between the recall item and the tone are fewer. So they manipulated how far the last item was from the probe item. It was either immediately before it or 2 or 3, 4, 5 or 16 digits before it. So they manipulated the interference aspect of it by manipulating the number of intervening items. But here is the interesting thing. So it was like two items in between, 4 items, 6 items, 8 items, 10 or 12 items in between. But here is a more interesting thing. They also manipulated the time. In other words, for each, let's say, if only 2 items, they manipulate time. There is T1 and T2, where they got more time at one point and fewer and less time in the other condition. How is it possible? But the way they did it is they presented the same 16 digits at 2 different speeds. One group heard these 16 digits very fast. So they would hear the 16 digits at a speed of 4 digits per second. So something along these lines. 084 1609 5537 72478. You see that? The other group, on the other hand, would hear these sounds at a slower pace. Same number of items presented at different speeds. You see that? It would be something like 7, 0, 8, 1, 6, 0, 9. We see the idea. So same number of items were either presented at a faster speed or slower. So that's how they manipulate both time and intervening items. So between the recallable item and the tone, the two things that happen. First of all, the time has passed, and this time passage was either one group was same time, the other group it was fast or slow, more or less time, and they also manipulated more digits, right? It's very interesting. I love this study. We'll talk about the results in the next slide. So here are the results. The x-axis is number of intervening items. Remember, the number of items between the tone and the probe item were either 2, 4, 6, 8, 10, or 12. And the y-axis is the relative accuracy. And you can see there are two lines here. This is the line for items presented at 4 digits per second, the fast condition. And this is 1 per second slow condition. In other words, here the information was spent for less amount of time. Here the information was held for a longer amount of time. Make sense? So they manipulated the time in this sense, and they manipulated the number of items in that sense. If information is lost by just passage of time, you should see these two lines being different because passage of time, if it's a factor. But you can see these two lines are almost parallel, suggesting that the information lost is not because of the difference in the passage of time. Rather, it is because of the difference in something else. What was that something else? That something else was the number of interfering or intervening items. The more the interfering items there were, in other words, the more the number of items between the probe item and the tone, the worse the accuracy of recall was, irrespective of whether they had more time or less time, suggesting that the reason you lose information from short-term memory is most likely through interference than decay. It doesn't mean that you can't lose information through decay. It's just that it's more practical to think, and it's more reasonable to assume that you lose information through interference because new information comes and erases the old information, and this process continues. Well, this brings us to the end of 7.1, where we talked about SAS as short-term memory. Thank you very much. I hope you liked the video. Have fun learning.